Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, great. So interrupt me whenever this is all very relaxed. Good. Okay. So networks for the past few decades have been configured this way, right? You've got various internal configurations, you've got the web, whatnot, but most importantly, you've got these boxes that sit there that perform various pieces of functionality. And for example, a NAT, right? You all know what a NAT is. Everyone has a NAT now, right? Everyone's house now has a NAT. Right? What does a NAT do? Someone, what does a NAT do? NAT. NAT. No, not you, man. Be quiet. One of you, NAT. What does a NAT do?
Yeah, it's translation.
Yeah, it translates addresses. Why do you need one? So that you can have lots of people inside one share an address, multiplex an address. Okay. And then you have, firewalls that do various sort of requests and things like that. And so you can get these kinds of, in fact, there's whole websites dedicated to, drawings that people make, sketches sysadmins make of their networks, right? So they can share their network configurations with each other. And of course, now and then these network configurations don't work. So you go to these wonderful sites like, networkforum.com, think, Cisco, think again, right? And people will post these questions and they all start with some sort of frowny face, which means help me, right? I've been trying to make this work, I've been trying to make that work. And of course, this is the internet, so as usual, there's like a thread after thread after thread after thread, and there's all these discussions, right? Now, these boxes have traditionally been, so I put up a Cisco thing because Cisco is one of the behemoths in this field. These boxes are traditionally configured in a language called iOS. It has nothing, of course, to do with your cell phone, to your mobile phone. It's Cisco's operating system for this kind of stuff, right? And so code in iOS looks like this. And it looks all very homogeneous, but it's actually not because it's doing several different things. So for example, we're setting up various interfaces here. This part is setting up a static route. This part is setting up a NAT, and this part is setting up an ACL. And so there's all these sub-languages that are somehow combined into this one language. Okay? Now, what does the box actually do? Well, you have to understand exactly what iOS does. So we worked for several years on static analysis tools for being able to analyze iOS policies. And usually when I used to give talks about this in networking fora, usually first thing was, wait, you mean you can parse iOS? It turns out like even parsing this thing is, like a bit of a headache, right? And those of you who actually worked with iOS know it's just all of this is just completely painful. It's locked away inside Cisco. The specs are all, kind of what. In fact, one of the ways we engineered the semantics is we went on eBay, bought a cheap Cisco box, and sent enough packets at it, try to figure out what it does, because that's as good as reading the Cisco documentation. Okay, so first of all, it relies on these proprietary languages, and the second thing is if you want to change something, like if this is not the functionality you wanted, you want to implement a different system of some sort in your network, well, good luck, right? Because if Cisco agrees, they'll put it inside the iOS language. If they don't agree, you're out of luck, right? So those are two problems. There's another more subtle problem, which is there's some goal. Those of you, anyone here has administered a network at some point? Other than your home network. If you're trying to administer a larger network, you have some goal as a network administrator. There's something you're trying to achieve. But the way you achieve goals is you have to write some configuration on this box, some configuration on this box, all these configurations that somehow collectively have to achieve the goal you're trying to achieve. Right? So basically, this is distributed programming without the benefits of Rama helping you. Right? That's one way to think about it. So all these configurations have to somehow conspire to achieve what you want. So in the past about 5 years, there's been a growing trend in networking to say this is not an okay way to build our systems. Amongst other things, this also dissuades people from innovating, right? You come up with a new protocol, well, how are you actually going to implement this? You can't. So there's a new trend that says instead of having these very powerful boxes, we'll instead have very weak boxes. And what they will do instead is when they get a packet, they'll forward the packet off to a central controller. Now, this is, I should emphasize, very strictly a logical model, right? The implementation differs from this. But the logical model is you send things off to the controller. So you have these switches that are really dumb. Okay? They don't have a big complicated language. Of course, that's version 1, and version 2 they always do end up getting more and more complicated. But at least the idea is that you have these dumb switches. All the decision making happens on the controller. And all that the switch does is, instead of having this big iOS program, it simply gets instructions from the controller, remembers and executes those instructions. Okay? So this is the way networks are increasingly being built. For example, there's some famous success stories coming out of companies like Google where their back-end systems now use this kind of configuration instead. Okay? And this is called software-defined networking. And if you talk to networking folks, they like to say, look, this is great, right? Finally, we get the power of software in your network, right? This is like an actual slogan that people use. And it's great because it means that central controller can now be, it can be distributed. You can use Paxos. It can use, Rama's ideas for like how to build these things and how to get them to be reliable and robust and scalable and all that stuff. And it's wonderful, right? Compared to the bad old days. Now, of course, as a software person, I saw this and I said, great, okay, all of the problems of software are now in your network, right? It used to be that we had these nice compact languages, right? It almost makes you sentimental for things like Cisco iOS, because there you had a language that had some manageable complexity, and now all the problems that can attend software now happen in the network as well, okay? So, to refine this picture a little bit, there's really a very important distinction to understand between what's happening at the controller and what's happening at the switches. So this is typically called the control plane because it's the thing that's making decisions about the behavior of the network. This is the data plane, which is the thing that's actually implementing those decisions. It's the thing that's actually implementing what happens to each individual packet or each flow inside the network. Okay? But there's actually kind of a third plane here, which is this sort of program state as well, right? Because this program is going to remember things, like even take a NAT, right? It has to remember the NAT state and propagate the NAT state. So there's also probably some program state. And to make these things, reliable and robust and performant, these things are actually quite complicated. All the usual sort of distributed system stuff comes in here. So really what you have is 3 tiers. You have a data store, you have control logic, and you have forwarding rules. And now this picture starts to look a little bit familiar, right? Because we're used to 3-tier architectures. We've seen these before. One difference is, there's actually sort of 2 key differences. One is that these forwarding rules are sort of much lower level. Right? If you think about the web, the third tier is JavaScript, which is fairly high-level language, and I know we've all been there. But it's still a real programming language. This thing is not a programming language, right? It's just a bunch of dumb rules about how to handle individual packets and flows. And also, there's no UI here, thankfully. Right? This thing has to do with CSS and JavaScript and like things flashing and jQuery and whatnot. There's none of that here. Right? The forwarding rules are a really dumb layer. So this is still nevertheless a 3-tier architecture. It's just important to understand that the third tier is really quite different. The other 2 tiers are fairly similar. So now when I say problems of software in your network, what kinds of problems might you have? Well, there's a whole bunch, right? So one thing is, you've got multiple tiers that are making decisions about packets. There's this tier, which is enforcing the decisions, but there's this tier, which is kind of like actually determining what should happen, and these things could end up inconsistent. Right? You might have a switch that forgets to notify the controller because it got the wrong kind of policy downloaded to it and fails to notify the controller when a state update, for example, is needed. Of course, for performance reasons, you also don't want to notify the controller more than necessary, because then, like this switch is, trying to switch packets, right? And you're trying to watch a Netflix stream, and if every Netflix packet you went over to a central controller, you're completely hosed. You're not going to be able to watch any movies, right? And the other thing is, this code is now, general purpose programming, and we know that can be a bit of an entertaining activity, right? So any bug that you might make in Python or Haskell or Java or JavaScript, because people write controllers and all of these things, now you have to deal with all of those problems. There's actually one more very subtle problem, okay? Which is, remember, let's think about the web by analogy for a moment. This tier generates code for the other 2 tiers. Right? Think about SQL injection attacks, right? Where do SQL injection attacks come from? They come about because people didn't do their quotations properly. But in the first place, they were generating SQL. That's the key thing. Whether they did safely or unsafely, they were generating SQL. You have a program written in around here, say C# rather than Java. But you have a program written in C#, right? And it's generating SQL code. It's generating JavaScript code. The same thing is happening here. Right? These are program generating programs that are generating code in flow rules. in the language of flow rules. So if you want to now apply all this wonderful verification methodology that we have for programs in these languages, well, that's not enough, because most of the interesting action is actually happening one tier below. So whereas you might, in many cases, you can think of the web as sort of this cosmetic tier, right? You're just generating some JavaScript that maybe does some UI stuff, but all the core logic is on the server. That's no longer true here at all. I mean, it's not true in many web applications either. But to really understand the bugs that I'm talking about, you have to be able to talk about the generated code from this central controller. Okay? And verification methodology is nowhere near there, right? I mean, most of these assume that these are whole programs and we're not going to worry about generated code and so on. So it's actually quite challenging to think about this. Okay? So we have these three tiers, and now I want to tell you about a new programming language we've been working on called Flowlog. And the first key thing about Flowlog is it's what we call a tierless language. So this is an idea that people have tried in some other domains. It's been tried in the web, and it's usually a complete failure. And it's a failure because nobody knows how to generate, user interface code from a tierless programming language. We don't have that problem, as I just explained. We don't have to worry about generating UI. What happens on the switches is really dumb, and it's completely within the logic of the program. There's no UI and weird complications like that. There's no jQuery and things like that to worry about. So it's a tierless programming language, which means you write a program as if it's running on the central controller, and the other parts are generated for you by compilers. Okay? So in particular, there's a sophisticated compiler that's going to generate code for you. And the more important thing, so I could spend a lot of time talking about the compiler, which is interesting in its own right. There's some good partial evaluation going on underneath. But the more interesting thing is that we have cross-tier reasoning support. So I'm going to give you a little bit of a sense in the rest of this talk about how Flowlog works. I'm going to show you a small program, so just to give you a feel for the flavor of the language. But then I want to talk more about program reasoning, because I think that's the really cool thing here. Okay? Good. So again, remember, you can interrupt me with questions. You're all nodding, which is a bad sign. Okay, too much good. Somebody not nodding for a change.
This may be a tough question, but
go for it.
When you say that you don't really, so when you're verifying a program, you are actually verifying the generated, you have to verify the generated code. So if you are verifying the generated, so suppose you have to verify a property for the generated code, can't there be an equivalent property in the program generating program which
Yeah. So the thing is, where's the nearest whiteboard I can use? Can somebody toss me a marker, please? Great, thank you. So let's just say that we've got some C# program over here that's running on the server, okay? And there's a switch here, and flow rules are going to be generated to the switch, okay? So the structure of this, so you're right. Certainly I can look at a set of flow rules and use a flow rules verifier for that. There aren't very many yet, but that's because the area is in its infancy, but you can assume that there'll be pretty sophisticated verifiers at this level, okay? But the problem is, this thing is generating new flow rules sometimes every second, okay? So which flow rules are you going to look at? I mean, it's constantly updating because it gets new packets, and it says in response to this packet, oh, somebody just started watching a movie. Oh, somebody just left the room. Oh, this thing happened. Oh, that thing happened, right? There's constant traffic, or they're under attack, or a new attack just started up, right? So it's constant traffic on the network, in response to which new sets of flow rules are constantly being generated. So you can't really talk about, this is actually an interesting contrast again with this sort of JavaScript world, where the code you generate tends to be somewhat static. Right? I mean, you import a bunch of jQuery libraries, you generate some code. There might be some small changes, but by and large, the code you're generating is pretty static. Here, it's very, very dynamic. So it's not very effective to look at the flow rules and try to do the verification at that level. You want to do it at this level. But now this thing is no longer just C# code, right? It's C# code that, in a very naive sense, is probably doing this, right? It's got a bunch of printf statements, effectively, morally, the equivalent of a bunch of printf statements that are generating flow rules, right? And it might even be, dynamically generated strings that it's generating, right? And that is what you have to somehow make sense out of. That's the part that's tricky. Does that make sense? That's a really good question, but hopefully that answers the question. Okay, good. Yes?
I have another question about the target. So, do you assume that Flowlog completely takes over the network, or can it live together with code? Use generators.
Great question. Great question. So we are actively designing the language so that we don't want to assume it will take over the network. Okay, we don't yet have a good interface specification for the problem is we want to be modular, but to be modular you need interfaces, and the networking world is not there yet to talk about what those interfaces might look like. But we're very careful to, as much as possible, not assume we know the whole world. Okay, but it's a subtle question, right? Because, but yeah, we don't want to assume that there will only be Flowlog in the world and no other traffic, and we'll get to see everything. That would be unreasonable. The thing to do is, if there's independent traffic, of course it doesn't matter, right? It's when there's somewhat dependent traffic, then you need interface specifications to talk about what things you will touch and what things you won't touch, and which programs. Like if you have a program that's counting every packet in the network, well, that program's not going to work anymore, right? But a program that's doing something that can assume that some traffic it doesn't see, well, that's okay, right? So I think that's a very interesting language design question. We're not quite there yet because the whole community is sort of slowly getting to that point. Okay, all these modularity questions are very pressing and not yet. Yeah, good. Other questions? Great. Okay, so let me show you a little bit of Flowlog code. Let's do a NAT. Okay, let's write some code for a NAT. So I'm going to walk through this code line by line. The thing to understand is you can think of Flowlog, if you've ever seen a language like Prolog or Datalog or something like that before, the name is meant to be suggestive. Use your intuition, okay? So the idea is we have relational programs. So here is a table, it's a NAT table, and it's recording what is being natted to what, right? What's the incoming traffic and what's the new name for the outgoing traffic? That's basically what that means. I have a variable that tells me what the next free port is. And now, when a packet comes in, I look to see whether the packet is already in the NAT table, whether that source address is already in the NAT table. If it matches, that means it's a flow I've already established. If not, right, the negation of that means it's a new flow and I need to create a new NAT for it. Okay, so if it's an existing flow, what am I going to do? I'm going to forward the new packet. I'm going to forward the packet to the NAT port I've already recorded in the table. If it's a new flow, I'm going to do the same thing, except I'm also going to add the next port to the NAT table, and I'm going to increment next port. Okay? So, more or less the definition of a NAT. Okay? One direction of a NAT. And that's the whole thing. This is actually live running code. This actually implements a NAT, and implements a fairly efficient NAT, because when it goes through the compiler, it makes sure there's no extra packets being sent, and that every packet that it needs to see, it'll see, and no extra packets get seen. Okay? So that's a whole working program. So of course there's a whole system behind it. It's implemented on top of a bunch of libraries. This is this proactive compiler that I said that generates packets before essentially generates rules before they're needed, which means we can run at the speed of hardware, right? Whatever the hardware can do is the speed. When we measure, when we benchmark, we're as fast as competing systems because of this proactive compilation, and it produces flow tables that are not too large, which is another thing that people usually care about. Okay? So that's a short introduction to the language. Now I want to talk about the interesting part to me, which is the reasoning side of it. Okay? So let's go back to these problems I talked about before. Right? So the thing to note is many of these problems just disappear. If we get inconsistent packet handling, it means there's a bug in the compiler. Right? It's no longer the programmer's problem to deal with that, just as they currently don't deal with compiler bugs. They report compiler bugs and compiler bugs get addressed. Right? Failure to notify the compiler, failure to notify the switches, too much traffic, all of these things automatically go away. The program generating program goes away because, as I just showed you, the code is tierless. It's just written from the point of view of the controller. Generating the code to the backing store and generating the code that goes down to the switches is done automatically, so you just don't even write that code, right? There are no printf statements in the code that I just showed you. Okay? And now this part is interesting because we still have a full-blown programming language. The experiment we're doing is we are limiting Flowlog to be non-recursive data log. So this is a weaker sub-Turing complete language. It gives us some very interesting, useful properties in terms of decidability. And we're trying to see, it's really, when I say experiment, I really mean the word experiment. We are trying to see how far we can push it, how many different networking protocols and how many different networking applications we can write in this weaker language. Maybe 3 years from now we'll say, yep, this is the limitation and we can't get past this, so we have to fix the language, or maybe not. I don't know. Okay? So with these kinds of stupid errors out of the way, now we can talk about, of course, we're still going to make errors, but now we get to system-specific errors, right? For a particular application, what kinds of errors can I make? And there's all sorts of ones, right? Well, I have a network configuration. Will the web request get through? Can I ever route packets in a loop, right? This is something networking people always care about, right? You don't want to end up sending packets in infinite loop. Will NAT be performed on all packets? Can packets, et cetera, et cetera? You can imagine a whole bunch of properties like this.
Sorry.
Yes.
I don't have a full intuition for what the abstraction. How should I view Flowlog? So,
Okay.
you have tables.
Yep.
And what do you?
So you have a table, okay? That is a specification of what your backing store looks like.
Okay.
Additions to the backing store, like over here, I insert a new row into the table. I insert into NAT.
Right.
Okay? That insertion is stated by the programmer. The actual implementation of that in terms of SQL statements or whatever else happens by the compiler. But more importantly, the way you write your program is as if you see every packet, right? On TCP packet P, right, where it came from this position, and so basically, like, if the packet came over here, I have this clause that says on TCP packet P.
Like predefined types for this, or these are user-defined?
So some of these are predefined types, like TCP packet, but then you can define your own relations on top of that. Okay, so you can write new relations that basically implement higher levels of functionality. So, for example, here's a nice little example, right? I have slides sitting around if we need to get there. But imagine an application where you register your laptops with the system, with the campus police or your corporate police, right? Corporate security. And when your laptop is stolen, let's just assume you live in a world where you remember your MAC addresses. Okay, so you call the security and say this MAC address just got stolen. Okay. So the security staff have a program that's basically pretending it can read every TCP packet. Okay? If a TCP packet that comes in that matches a packet that's in this table, then now it has to activate. It'll call the police and say, hey, we just located it. In fact, it came from this base station, so maybe it's in that geographic location of the building or something like that. Okay? That's the idea. Now, the thing is, we don't want to see every packet. If we see every packet, we'll never get anything done, right? Because we want packets to be handled locally, not all of them coming to the server. So, in fact, what happens is this code essentially gets compiled down to work on the switches. Meaning the switches see every packet, but in this particular case, if the NAT table is not going to be affected, right? So the first time you get a new packet that's not been natted before, you have to notify the server, it has to do something with the persistent state and so on. So that's in the new flow case. In the existing flow case, there's no reason the server needs to see this at all. The controller doesn't need to see this at all. Okay? So what happens is this code essentially gets compiled down to the switch and says, if I'm one of these NAT things that I've already seen, forward it along in the following way. Rewrite the headers in this way and forward it along. And it simply never even comes to the controller. So the programmer sitting at the controller has programmed this tierless abstraction which pretends they see every single packet. The compiler makes sure that the controller sees as few packets as possible. So that's what we're calling the essence of the tierless abstraction.
Okay.
Did that make sense?
Yeah, so the tierless part makes sense, but
okay.
I guess it's the bigger global picture. So I guess you have a model for what routers and all these things do, right?
Yes.
So that part is fixed in the language. So that's an assumption you have a stream, incoming stream and outgoing stream.
Yes. Yes. That is fixed. That's fixed, and that's given to us by the sort of SDN protocols, right? That's the part nobody wants to reinvent. Okay, so that part is fixed, and the assumption is there's a stream of packets, and every packet contains some metadata with which I can make various decisions, right? Okay, and then you program as if you see every packet. Good. Yes.
One thing, when this, it may not be that problem, but in this whole TLS language, it's almost lost what information gets to the controller and what information is handled by the router.
Let's be careful there. It's not true what information. The information that's in the controller is this.
Yeah.
Okay? All the tables that I declare are the information.
What packet?
What packets is lost. That's right. That's exactly what you're giving up, is knowledge of which packet comes to the controller.
Yeah.
Okay, now I could imagine that, okay, why is that a problem? For example, my network isn't going as fast as I would like. Well, one good place to look is maybe too many packets are coming to the controller. Okay, that's something that the runtime system can give you. So our runtime system, so it's easy to maintain counters. So runtime system can maintain a counter and give you, for debugging purpose, say this is how many packets came through, and you that's relative to the total number of packets. That's an absurdly high ratio. What's going on? And then we have some technology in the stuff that we did for iOS where we could do something called rule blaming. So you can ask, like, why is this thing happening? Tell me which rules seem to be responsible for this behavior. So the same technology we haven't applied it here, where you could say, I'm getting too many packets, and it's like, that rule over there is the thing that's causing all these packets to happen. And then you can say, what is it about the way I've written this rule that's causing, all this, causing excess traffic? So you're right. The language does not let you see which packet came to the controller because it pretends every single packet did, but of course in practice you don't want that. And then we think of that as a debugging metadata activity instead.
Yeah.
Does that make sense?
Yeah.
Good.
One more thing.
Of course.
So this TCP packet thing, so it's not a language construct, right? You define it.
It's a relation that's defined in, yeah.
Yeah, so the thing was that, so how I see this is like similar to a packet filter.
Yeah,
So
yeah.
Your idea of non-recursive data log is that packet filters are generally simple and you don't need full Turing complete languages to write them.
So yes. Go on.
Is that these TCP packets and everything else, these small abstractions you create may require full.
So this is great. Yes, you're right. You can think of this at a very high level as packet filter is a perfectly good way to think about it. So I have two responses to that. So recursion is actually interesting. So if you think about, like, one of the things that a network needs to do is it needs to figure out, like, what all of the routes are that are available inside a network, and periodically they will send out, like, new ARP requests to figure that out, right? Well, so that's transitive closure. Transitive closure is recursion, right? So how do we reconcile that? So it turns out we can actually use the network to provide us with recursion. I send a packet out, right? That packet's going to come back to me as a new packet. Well, that new packet just gave me a loop that I didn't have to express directly in the program. So it's a little bit of a fake, but it turns out it gets you pretty far, because this kind of transitive closure is an important part of networking. But the other answer to that is Flowlog is, so typically when you have a DSL of some sort, you have some great big, Turing complete language, and then in the middle of it you're allowed to put, like, sub-Turing complete pieces. Right? This is, I don't know, SQL, and this is, some selector language or something like that. You have these little raisins of sub-Turing completeness inside. We're looking at Flowlog differently. We're saying, look, Flowlog is this language that is not Turing complete, but we have an explicitly defined callout mechanism. Okay, with typed interfaces for callouts, so you can call out and you can say, look, I've already got some Java code that implements some routing package from a routing algorithm. It would make no sense for me to re-implement that in Flowlog. So you can call out to these things. The interfaces, you expose a table to them, they populate the table and give you back the table, and then there's some work about what table means for these programs. And so we're essentially inverting the standard picture. Right? So when you need to get to those big computations that are algorithms that have probably this is not the right language for, you call out, you have to provide a spec of what that's doing so that the verifier can use it. That's the trade-off. Does that make sense? Great.
So these are like user-defined functions in SQL.
Yeah, exactly. That's exactly the intuition.
But when you say spec, you want a functional spec?
Well, it depends on what you need a spec as much as the verification you're trying to do needs, right? Okay. So that's the usual trade-off. Yeah. But it's very much SQL is a good intuition for what we're trying to do, and those are stored procedures in SQL, right? Like that. Yeah. Okay. Good. All right. Questions answered? Great. Okay. So we were talking about some kinds of properties, right? And what I want to note is that I've written 4 properties on the screen, but they're 2 sets of 2 very different kinds of properties. The first 2 are about my network, which means you can't reason about this without knowing the actual layout of the network, right? So this is topology dependent reasoning. It's network dependent reasoning, right? And I mean, the thing is, when you start doing network-dependent reasoning, well, you need a statement about the network, and this is where things like, state explosion tend to become a bit of a problem. And so we don't have an interesting story here. We've been using spin for model checking these kinds of properties. You give it the topology as an input, and then you go off and do sort of usual model checking. This is an interesting question. It's not where we've put our emphasis in, so I will leave this as sort of an open question for people who want to think about this and think they have some good tools for doing this kind of reasoning. Because we're trying to do the other kind of reasoning, which is when you get to these kinds of properties, they don't say anything about the network. So if they're not a statement about the network, what are they a statement about? About the program. They're just program reasoning, right? So there's a whole bunch of network agnostic reasoning that says, I have a controller program, and no matter how many nodes come and go, and no matter what the shape of the topology is, I want to know that this program has the following behavior, right? And that's just back to good old program reasoning. And there are many properties that fall into this kind of category, right? So this is where our emphasis has been. So I'm going to take out that first property here and observe something interesting about it. So what do I say? I've got some controller, and it replies to ARP requests for addresses that it's cached. So if you don't know what ARP is, don't worry about the details. The point is that this is the kind of property you might want to verify about an ARP, right? And now I'm going to color code it. And you notice that the caching is a statement about the database. The requests are a statement about what the forwarding rules are doing. And the controller will reply as a statement about what the control logic is going to do, right? So because I have this tierless abstraction, I can state these kinds of properties very naturally, even though they cut across all the three tiers. If I did not have a tierless, I can still state a property, right? I mean, anyone can state a property, but to verify this property, when I've got some of the property is a statement about what that combined string is going to be doing. Good luck with that. Right? So this is where this idea that we'll write the program as if we're just sitting and seeing every packet gives us a huge amount of power, right? Because this kinds of properties are much easier to discharge over this sort of packet filtering model. And many properties have this kinds of characteristic where they really talk about 2 or even 3 tiers at a time. Okay? So the way we do our verification is actually pretty straightforward. These are, this is basically a sub-language of first-order logic. So you can compile it down into multi-sorted first-order logic. There's a tool called Alloy, which takes first-order logic and turns it into SAT problems. But there's one key problem with Alloy, which is because first-order logic is undecidable, well, like most of the things you care about are not decidable, you have to specify domain bound sizes. But most of the things we care about in Flowlog have a particular quantifier structure that's a sub-language of first-order logic called effectively propositional first-order logic. And there's a beautiful theorem from the 1920s, actually, that will basically construct a domain bound for you that's a sufficient domain bound. So you can get sound and complete verification even though you're using first-order logic because you're using the sub-language. Okay? And we have an extension to this sub-language that basically deals with multi-sortedness, and so we can get sort of even more bounds for even more kinds of programs. Okay?
So do you lose this if you add recursion? Is that?
Yeah. So once you start adding more, so there's now some results we're finding that not general recursion, but if you had transitive closure, you can get back some bounds and things like that. But yeah, that's one of the reasons why we keep the language weak, to see how far we can go. Right? So the verification times are actually quite small because these times are pretty robust because they are statements about the program. They are not statements about the system that's running. Right? Adding more nodes is not going to make any difference to this whatsoever. So examples, either verifying or finding counterexamples. And the nice thing about using Alloy is it also gives you these little pictures that show you like counterexamples. The reason we're able to get small pictures like this is we've done a bunch of independent work on minimizing scenarios. So taking first-order logic solutions, minimizing them and giving you a principled way of stepping through them, showing you in terms of entailments, even the provenance of individual facts, like why is this fact in this model, and we can give you a provenance for why that fact is there. So this is work that we've been able to slap onto this, so we can actually give people like nice counterexamples. Okay? And I want to talk about 2 particular kinds of properties that show up in practice that are really, that we can do a lot of good stuff with. One is what we call inductive properties. So take the NAT again, right? Remember, there's this NAT table. Right? The NAT table was basically an injective partial function, right? That's the state of that table. And what you want to know is, if it started off being a well-formed table, after a packet arrives, it's still going to be a well-formed table. Because one of two things happens, right? Either the packet arrives and it's known, so the table doesn't change, or the packet arrives, we add something new, and you want to make sure that this injective partial function property is maintained, right? So you want this property, you want this to be a statement about the program. What we do is we use Flowlog to verify the stepwise property, right, using the verification technology I just told you. The initial state is pretty easy to verify, and essentially we do the inductive step outside the tool, so there's no tool that does the induction for us, but that just follows because we've got the base case and we've got the inductive case, and just by the laws of induction, we get the inductive property for the program, which is actually a nice way to split the problem apart, because it means we don't need a prover that's strong enough to prove induction, right? Because then we'd have to go into theorem prover land and things start to get more complicated. Another kind of pair of properties that I found very interesting is the following. So here's a statement. If the table is consistent, so consistent meaning roughly injective partial function, before the packet arrives, it will be afterward, right? That's a statement about the preservation of the state of that table. The other one is, if you have a consistent table, either it'll forward, or it's going to signal out of, basically I've run out of ports, right? That's always the possible runtime exception. Otherwise, it's going to forward. So that's a statement that if you have a consistent property, then you are going to make progress. The program is going to actually do something good. Well, this progress preservation, we already know this is a classic structure, right? Type soundness theorems have been doing this kind of thing for a long time. So essentially, this progress and preservation, each of which we can prove using our Alloy infrastructure, basically gives us a kind of soundness theorem for a NAT. So this is something we've started to explore, because people don't usually think of network protocols as having soundness theorems in the sense that a type system does. And we're starting to explore this question about how many of these protocols can be broken up in this way, and we can actually verify some sort of notion of soundness for them. Okay? One last thing I want to talk about is property-free reasoning. Right? We're all sitting here, either PhDs or soon-to-be PhDs or long-time PhDs or whatever. And so, you want logic statements. You go to Cedric and he'll throw more logic at you than you can possibly count. Average developers aren't trained in logic, don't care about logic. Right? What they want to know is they want to know something about the workingness or non-workingness of their program without having to go through the rigmarole of formal property statements. And in particular, verifiers are kind of useless because without a property, they just sit there. They don't actually do anything. Right? Even Cedric's verifiers just kind of sit there without property statements. So there's a very useful kind of property-free reasoning that developers care about, which is simply comparing the behavior of multiple versions of a program. Right? This is, in fact, what we all actually do when we're writing code. We have a program that works, right, for some definition of works, and then either we do a bug fix, or we get some new feature, and now we have a new program. And what we want to know is, we want to transfer the faith we had in the old program into some sense of security about the new program. Right? It's about transference of knowledge, which means you can think of this as a comparison between those two programs. What changed between the two? But of course, what we care about is semantic difference, not syntactic difference. Syntactic differences, that's Git will give you that, right? We care about the semantic difference. And once you have this, you can do a bunch of things. Like you can say, look, I've got two possible configurations for my system. Which one should I use? Or I've made an upgrade. Is the upgrade doing exactly what I thought? Meaning it's doing the things I wanted, but also it's not doing the things I didn't want. This is the thing that humans are really bad at thinking about, right? Think about it. When you write code, you add a new feature, you write tests for that feature. You don't write tests for all the things that you expected to not happen as well. We're really bad about this kind of reasoning. You might want to know about hotspots, right? We talked about blaming particular rules. Like, I made a small change, I expected to see a small semantic difference, I got a large semantic difference. What changed that's causing a large semantic difference? Sometimes you refactor the code, you just clean up the program. Well, the behavioral difference between those two versions had better be 0. The syntactic difference might be large, but the behavioral difference had better be 0. Right? So there are all these kinds of what-if questions you want to ask. And we did this in the previous version also for iOS policies. And somebody found another use for it that we had not anticipated, which is mutation testing. Because when you do mutation testing, remember, what you do is you mutate the program, and you want to make sure that you have a true mutant. A true mutant is one that is semantically different. because you might make a mutation and it actually change the behavior. So if you have a quick procedure for checking that something is semantically different, well, now you can actually do mutation testing. That's the oracle you need for mutation testing. Okay? So this is the other thing we've been building for Flowlog. So you can take two programs and again use this alloy procedure. Basically, what it'll spit out for you is in what scenarios, right? Remember, it's constructing first order models. So basically, it's giving you concrete scenarios in which the two programs will diverge in behavior. So on this kind of input packet, it's going to do this. On this same kind of input packet, the other version is going to do that. You can also ask in what scenarios will the program transition to different states. And again, this also works very quickly. This is another thing that gets to exploit that Bernet-Schoenfinkel theorem, because all of these property statements in this change impact all fall into that class again. Okay? So last thing I want to talk for just about 1 minute is talk about this transition from just SDNs to Internet of Things. So one of the things, as you all know, is happening is we have these switches, but we also now start having smart devices. And I think one thing that's becoming especially interesting is this, until recently, configuring these networks these networks of Internet of Things was just this nightmare, right? You got to run cable, you've got to serial port, and then set this up and install a driver, and maybe it works and maybe it doesn't. And now there's a whole new generation of Internet of Things devices that are coming out that are basically web addressable. I don't know, has anyone here played with these, by the way? Web addressable, which systems have you tried?
I just played with some lights and cameras. These are, there's a startup in India which is manufacturing them. It's a friend of mine.
Okay.
So, these are basically small components where they have a very small Wi-Fi.
Yeah, right, exactly. So they give you like a RESTful interface, that sort of thing?
Yeah, so they have a controller through which you can.
Yeah, okay. Yeah, so this is something we're noticing in the US as well. A bunch of these startups that are now producing basically RESTful APIs for being able to talk to these devices, right? So now the whole configuration nightmare is mostly gone, right? I mean, it's kind of ironic, right? I'm sitting here on my laptop, the device is over here, the way I communicate with it is go over to California and back, but that's the nature of the world, I guess. So you've got all these lights and cameras, whatnot, and now you can have an SDN style controller here, which basically again gives you a tierless abstraction for programming on these devices, right? So we've been taking Flowlog and translating it to also work over these kinds of device networks. So you can do things like this, right? When I detect a motion, so now this is a domain specific type, right? So if I have a motion sensor, it provides motion detection tuples, and I might have camera on tuples and so on, right, for each kind of device. And so when I detect a motion, maybe I'll turn the camera on, and I'll either reset the timer or I'll start it with a camera ID and some timer of say 5 seconds, and when the timer expires, I'm going to turn the camera off, right? So every time I see a motion, I'll run the camera for at least 5 more seconds, right? That sort of program. So we've been starting to play with Flowlog. This is, again, actual live code that runs right now using a system called Spark.io as our backend. There's a lot of interesting new challenges here. First of all, these things are now heterogeneous devices, right? It's actually the case even in the SDN world. Academics don't really like to talk about it, but the SDN networks are also heterogeneous because you have these dumb switches, but you also have various kinds of middle boxes. But here you really cannot ignore the heterogeneity. A light is not the same as a camera, is not the same as a motion sensor at all. The other thing is, in the SDN world, the idea is that you won't have much computation running on the switches, right? They're going to be very dumb. They're just going to have some routing circuitry, and that's about it, like small, fast. But here, these are basically all Arduino chips now. So you can take some computation that used to run on the server and truly, honestly offload it onto the client, and which means there's now interesting policy questions. Right? How do I decide what computation should run where? Basically, there's trade-offs based on power, the amount of communication bandwidth, maybe the physical location, maybe the robustness of storage at that location, and so on. We would like to think of this as an opportunity to, again, program in a tierless way and have even smarter compilers that can take these kinds of policy issues and use the policies as a way of figuring out how to generate code for each of these switches, which are now IoT devices. And I think one of the things we're also going to see is a convergence between sort of this SDN style programming and IoT programming, because you're going to want, at least some people, I guess, are going to want situations where, if I sit down on my couch, I want the lights to go down and I want Netflix to come on. Or if I start up Netflix, I automatically want the room's ambient temperature to change and I want the lights to change. And so the network traffic and the IoT traffic are going to be talking to each other because each one is going to be telling the other thing something about the decisions that are being made in a physical space. Right? So I think partly what we're trying to do is to position Flowlog as a language where we can have all of these converging. Of course, I don't expect anyone's going to program their house using data log variant. We're also exploring some block-based, interesting syntactic design questions for how to design, using some HCI research, how to design an interesting interface to program these. But ultimately, at the bottom, of course, there'll be Flowlog. We just won't present it to the user that way. So
you could also have many different applications running in this setting, right?
That's right.
The interaction between them.
That's exactly right. That's exactly right. This is we've talked about this a little bit in the network space. It's not quite happened yet, but it's very clear that just as the cloud, you have a cloud box that's running all these different applications, right, multiple tenants, the same thing is also going to be happening on SDN controllers, and you're going to have lots of different protocols. And like I described the stolen laptop device manager, right? That's a program that you want running on your controller that's independent of the fact you also want NAT running on your controller. Neither one should be knocking out the other. So what are the forms of composition? So Nate Foster and company have been thinking quite a bit about like composition operators, but I would claim at a lower level. I'm more interested in the application level compositions because the issue here is not going to be are these two sequentially composed or parallelly composed. It's going to be more, what is the interface that this thing wants, right? It wants certain kinds of packets. And its I/O specifications wants these kinds of packets and it's going to impact those kinds of devices. This thing wants these kinds of packets, going to impact those kinds of devices. And how do these interfaces match up against each other? Are they in conflict or are they in harmony? Right? And if they are in conflict, even how do I get them to override? Which one gets to override the other? I think those are the high level, the composition questions that are absolutely about to happen. And the same thing's going to happen here too, right? Once you now throw IoT devices, I've got, my home router is I've got this box maybe, right? Little server running in my house that is both my intrusion detection server to make sure that my house network is not under attack, but at the same time is also controlling all the lights and sensors in my house. And how do these things work together? Well, I think it's going to be a really fun set of questions to think about. Many years ago, people, we and some other people spent a lot of time thinking about this feature-oriented software composition. Right? Software is a collection of features, and how do these interact with each other? I think all these questions are just going to come right back now. So I think to me, this idea of thinking of this as a tierless abstraction, like, otherwise I just don't even know how to begin to have a handle on the amount of complexity that's going to be in these systems. But at least that's me. Maybe other people are smarter than dealing with this kind of complexity. Other questions?
So I'm wondering about the configuration of the system. So whenever you add a new box or you turn on off the component or you add a laptop to the system, do you expect the program to change or to be recompiled, or is the program
No.
reacting to those? Or
it simply reacts.
So if I add a new NAT box or something, it will...
Well, so I should be a little careful with that, right? It depends on how much the program refers to particular devices. But the point is Yeah. So
rules for injecting program procedures whenever you add a device.
Yeah, so it's still the case that in some sense the program doesn't get recompiled. The program is a fixed entity, and maybe it has a rule that says if this particular MAC address comes online, and I happen to know that MAC address corresponds to Rama's laptop, right? So if that MAC address comes online, behave in the following way. The program is still fixed, right? The policy, that's a statement of policy, and the policy is fixed. But now the behavior of that policy changes because of the dynamics in the network, right? The laptop comes online, it registers itself, it contacts the base station forwards this packet and says, oh, I just got a packet from this MAC address. That means Rama's laptop is now there, right? Now I have to behave in this completely different way. So it's a static policy with dynamic consequences. Right? So the program, if you think of the program as a policy, it doesn't change. It's the consequences of the policy that change based on the dynamic state of the network.
Yes, as long as the program covers all the configurations.
Yeah. Now, if you choose to change the policy, well, of course, you're free to do that, right? Now, you want to add another rule that says Cedric's laptop. Well, now that's a change in the program. But otherwise, your program can even refer to very specific devices, but there's no reason for any recompilation or anything else, right? It just detects the event and says, new things online. Yeah. Okay. Good. All right. Thank you very much. Thank you for coming.